let's look at one specific example. This is an algorithm that's called rapidly exploding random tree, or an RRT. And the algorithm is here, and in fact, this is exactly the algorithm that you'll be implementing for the last project in this course. So here we're going to take a look at how it works. We're going to be a little informal about it, but you'll be making it a lot more formal as you go through your project. So let's see what this algorithm looks like in practice. In this example, is just to get a hang of it. We're not going to be necessarily terribly exact, but in the project implementation that will happen. So let's draw a relatively simple two-dimensional workspace. We're going to have Q1 and Q2. Okay. And I'm just going to put some simple limits on this. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10, and say that this is the limit of my workspace. And then the same thing here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. And I have a start point. I have a goal point. And I have some obstacles that are blocking my route. Okay, how do I get from the start to the goal using this algorithm? I'm going to use blue to draw the tree. So you can see that we begin by just saying the start point is in my tree. So this is the extent of my tree when I start. And then we go into this main loop of the algorithm. And I'm just going to use a simple Python command to just generate random numbers between 0 and 10. So let's start. Let's say I'm going to take 2 random numbers for my first point. So I'll have, and I'll be rounding to the next integer. So 7 and 7. 7 and 7 is right here. Okay. So then what this says, sample random point in C space, which I just did. Find the point in your tree that is closest to the new point you've just sampled, as this is the only point in my tree so far, so this is going to be it. Add branch of predefined length from your tree towards the new point. So I'm going to add a branch that comes from S and goes towards this new point that I've sampled of some predefined lengths, let's say roughly 1. And then we continue. I'm going to get 2 more numbers. So 1 and 7. 1 and 7 puts me right here. The closest point in my tree, let's say it's still S, so I'm going to get this branch. Keep going. 8 and 5. So 8 and 5, this is the point right here. The closest point in my tree is this. I'm going to try to grow a branch, but if I grow a branch that's of my predefined length, I'm going to realize that, wait a second, this new point intersects the obstacle. So instead, I'm going to make my branch as long as it can be without hitting the obstacle. So that's where I'm going to get to right there. Keep going. 1 and 8. So 1 and 8 puts me right here. So then I can grow from this point in that direction. 9 and 4. 9 and 4 is right here. And then what happens is I cannot really grow this point anymore because I'd hit the obstacle. So never mind. Keep going. 3 and 3. So 3 and 3 puts me right here. So then what I'm going to do is grow from the nearest point in this direction. Now you're starting to get a sense of how the tree grows. 1 and 7, that's right here, so I can just add a tiny little branch that goes like this. That's fine. They don't have to be necessarily too long. 5 and 7. 5 and 7 is right inside the obstacle. I cannot really grow that anymore because I would hit. 6 and 1. 6 and 1 is right here. Let's say that this is the closest point, so I'm going to grow in that direction, which would put me right here. Again, 6 and 3, so 6 and 3 is right here. This is my closest point, so I'm going to grow in that direction. 6 and 4, so 6 and 4, that's right here. That's inside the obstacle, but I can still grow up until that point. 1 and 6. 1 and 6 is right this, so I'm going to grow like this. 6 and 3, so 6 and 3 is right here, so now I can grow like this. And then there's this additional check, which so far we haven't done, right? It says while tree cannot connect to goal. So in fact, every time I add a new point to my tree, what I also do is I check, hey, can this new point connect directly to my goal? And then let's say that when I add this point, I realize, you know what, this line, this straight path line is actually collision free. At this point, the tree connects directly to my goal, and I'm done. Now I have a path that goes on the tree, and only on the tree, that goes from the start to the goal. Then what happens is I also realized in practice, oftentimes the paths that you get when you run an RRT will have a lot of zigs and zags, so I can do some shortcuts. In this particular case, I realized, hey, you know what? I can actually go, once I have this path, I can go from here straight to here without hitting anything, so I'm just going to shortcut like this. And then after I've shortcut, then I can throw away all the rest. And there you go. Now I have my path from the start to the goal, right? So the tree grows from the start. It kind of grows in all directions. It eventually finds its way between obstacles. It's OK if you explore in what seems initially to be like the wrong direction. Eventually, it finds its way around the obstacles, and you get the path to the goal. Right? And it's actually very important, this ability of the tree to grow randomly, to go in all directions, is very, very important, because oftentimes what happens is you find yourself trapped, right? So for example, in this case, what could easily happen is you have a different configuration. Let's say you have the same start and the same goal. So the start is right here, and the goal is right there, but maybe the obstacles look like this. And if that's the case, then if you just try to go towards the goal, which is what, for example, Cartesian control would do, you get yourself immediately stuck. However, a tree, an RRT, it will grow in all directions. And yes, it will find all of these paths that don't really go anywhere. But eventually, because it keeps growing in all directions, even in directions that momentarily these look like bad ideas. Wait, the goal is that, again, remember, you don't know the shape of the obstacles. All you know is whether a new point collides with an obstacle or not. So when you start off, going that way seems like a good idea. Going the other way seems like a bad idea. But the random tree, the stochastic algorithms, go in all directions. So eventually, even what initially seemed like a bad idea eventually gets out of the obstacle and can connect whereas all the paths that seemed like a good idea at the beginning are still getting stuck in all these dead ends, essentially. So this is a very, very simplified implementation, and production level implementations of RRTs have various subtleties which increase performance. For example, a neat trick is to grow two trees, to grow one tree from the start, one tree from the goal, and at some point check if those two trees can connect to each other. That makes computation faster and finding a path faster. There are many other subtleties along similar lines. But fundamentally, this is what an RRT looks like, and this is exactly the RRT that you'll be implementing for your project. One thing to point out, I've highlighted here the external calls. So what do you need in order to implement an RRT? And in blue, in this pseudocode, it shows what can be considered external calls to external tools. Obviously, you need a random number generator because you need to be sampling truly random points in configuration space. Most high-level languages these days will have a pseudo-random number generator, which is perfectly fine. The only other external call that you're making here, you're asking if a new branch that I'm adding to my tree, so let's say, you know, I have this point in my tree, I want to add this branch, does this intersect an obstacle or not? This is the only other external call that's being done, asking if a branch intersects an obstacle. I told you earlier that really all you have at your disposal is the ability to answer point queries. Does a point is a point inside an obstacle or not? How do you check if a branch intersects an obstacle? Well, very simply, you just discretize it. You sample individual points along the branch with however fine resolution you want, and you just ask individually, does any of these points intersect an obstacle? And then if any of the points intersects an obstacle, you know the branch intersects an obstacle, and you react appropriately in your algorithm. That's everything you need, right? So again, when you're doing RRTs, you don't have an actual knowledge of the shape of your obstacles. You don't know what they look like. All you know is that in this case, every time you try to grow the tree from here, this tells you, no, collision. This way, no, collision. This way, no, collision. This way, yes, you can go. This way, no, collision. This way, yeah, this is fine. This way, no, collision. And eventually, if you try enough of these, you find your way around the obstacle and you get to the goal.